So I'd like to talk a little bit about arc length. So say I have a function, a smooth function, f of x, on a, b, the interval a to b. Smooth just means that it's differentiable, it's continuous, and its derivatives are also continuous. And I'd like to determine sort of the length of the curve, the length of the graph of f of x from a to b. So imagine you had like a string or something, and you placed it on this curve, right? You put it right on top of this curve, and then you picked it up and you wanted to measure how long that string was. That's what the arc length of this curve is. So we want to determine the length of the curve from A to B. Okay. Well, we know how to do quite a bit in calculus now, but if you can think back to where it all started, when we were trying to determine the area under a curve, we decided to kind of break it up into a bunch of areas that we knew, which were rectangles, and that's how we sort of derived this idea of an integral. Same idea here. There are certain things that we know how to find the length of. In particular, we know how to find the length of a straight line. So we're going to do something very similar here. We're going to take this interval and actually this curve, and we sort of break it into a bunch of straight lines. So imagine I take, some endpoints and I draw a line. Now that line is not the same as sort of the curvy part, right, between its endpoints, but it's a pretty good approximation. And if I, keep doing this all along the curve, you can see that if I add up the lengths of all those line segments, I'm going to get a pretty good approximation to the length of this curve. And I know how to find the length of a line segment. So, if you remember the Pythagorean theorem, right? So if you take it's a distance formula that comes from the Pythagorean theorem. So if you make a right triangle here, let's see, what should we call? Well, for now, let's say this is A and this is B, whatever those lengths are. Then the length of the red line segment between, that first red line segment is just the square root of a squared plus b squared. Right, and that's just the distance formula, which is really just the Pythagorean theorem. Okay, so I want to make this a little bit more formal. Rather than using a and b, I want to kind of think back to what we did with integrals and Riemann sums, right? So what we did first was we sort of broke our interval from a to b into a bunch of equal lengths, right? And so and each length, each little width here of the subinterval we called delta x, which was like b minus a over n. N was the number of little pieces we broke our interval into. So above each of the endpoints of these intervals, I'm going to put a point. So I've already put a couple of points, right? And then I'm connecting those points with line segments, which are little secant lines to the curve, right? And that's sort of more formally what we're doing. And if we add up the lengths of all those line segments, we keep going, right, all the way, we're going to get a good approximation to the length of this curve. Okay, so each of these widths everywhere, they're all delta x. So actually, I know something about this right triangle. I know that this side is going to be called delta x. That's a good name for it. So that delta x stands for a small change in x. Well, it would make sense to sort of think similarly, about this length, right? So if I look at if I go to each point and I look to the left, I get different heights. And the change in height between the endpoints of the line segment is a change in y. So I might call that delta y, right? Now it's a little different, right? From here to here, that's one change in y. This line segment has a slightly different change in y, and this line segment has quite a bit different change in y. So each change in y is not the same, whereas each change in x is the same. So I can't just say delta y in terms of a change in y, but I can say, for example, this one I could call delta y1, right? And I could kind of do something here very similar. It's supposed to be a right angle, right? So let me zoom in a little bit. This is also delta x, and this I might call delta y2. Right, and so I continue this process on, and I have a delta y3 and a delta x. And, so I could determine I guess I could determine this length of this red line segment by just taking the square root. So the length of this little line segment is the square root of delta x squared plus delta y1 squared. Right, again, it's the Pythagorean theorem. And then you could find the length of this next line segment, right? It's a square root of delta x squared plus delta y2 squared. And in general, if we have right, so I'm thinking of this as like, x1, x2, x3, so on, right? And in general, I have sort of my ith subinterval, which I'm thinking of x having endpoints xi and xi plus 1. And if I look up above that, I get this line segment, and it has a certain length, which can be determined. Well, this is still delta x. I might call this delta y sub I. And so the length in general of the ith little line segment is going to be the square root of delta x squared plus delta y sub I squared. So what I would do if I wanted to approximate the length of my curve is I would sort of say the arc length. Maybe we'll call that L, which is the length of that curve of f of x, is basically what I would get if I took the length of each little line segment, which we found to be delta x squared plus delta y sub I squared, and we added all those up, right? So we just kind of added them up from 1 to n if we have n line segments, and that wouldn't be it wouldn't be equal to the arc length, but it would be an approximation, right? It would be a good approximation. So I hope that makes sense. So that's really the main idea, and then we want to kind of refine that approximation, and we can do that by actually having more subintervals. Right, so if we added more subintervals in here, oops, didn't mean to do that. If we add more little subintervals in here, they'll be closer together. These line segments will be a lot smaller, and when you'll see that when they sort of go together end to end to approximate the curve a little bit better. So what that amounts to is sort of seeing what happens as n increases, right? Okay, so we're going to do that, but first I want to kind of perform a little bit of algebra on this expression so that we can get a better idea of what it's really saying. Right, so we're going to derive a nice formula for finding this arc length. So I'm going to really focus on this for just a second. Okay, so the square root of delta x squared plus delta y sub I squared. Okay, so the first thing that I'm going to do is I'm going to actually factor out, it's really weird, I'm going to factor out a delta x squared, right? And so what's left is just going to be 1 plus delta y sub I squared over delta x squared. Right, you can check that if you redistribute this, it ends up looking the same as this. So we haven't changed anything. Yeah, and now, delta x is a positive number, so I can actually pull delta x squared out of the square root, right? Square root of delta x squared is going to be, well, it's going to be the absolute value of delta x, but delta x is this distance, which is positive already, so we don't need the absolute value. So we can rewrite this as delta x times the square root of 1 plus, and then I've got both the numerator and the denominator are being squared. That's supposed to be a square. Sorry, let's see. Okay. That's supposed to be squared. Yeah, so both the numerator and denominator are squared there, so I can write it as a whole expression, whole fraction. Delta y sub I over delta x quantity squared. Right, and so I want you to think about what this really is. This is a change in y over a change in x over the ith interval. So it's the slope of this secant line. Whoa, carried away. It's the slope of the secant line, right? So that's the change in y over the change in x is just the slope of the secant line. And we know that the mean value theorem for derivatives says that there's some value somewhere in between xi and xi plus 1, might call it xi star, such that the slope of the secant line between x sub I and x sub I plus 1, so here to here, the slope of that secant line is equal to the slope of the tangent line at x sub I star. So there's if I look up here, right, there's some place where the slope of the tangent line there is equal to the slope of the secant line. That's called the mean value theorem for derivatives, right? So let's write that down. So by the mean value theorem, for derivatives, there is an x sub I star in between x sub I and x sub I plus 1, such that the slope of the secant line is equal to the slope of the tangent line at x sub I star. And the slope of the tangent line, of course, is just the derivative. And this is true for every one of these subintervals. So in each of these subintervals, I can find, an x1 star, x2 star, x3 star. I can find all these, or x0 star. I can find all these places. They might not be right in the middle, right? They might be at the end. Who knows? But there's always sort of at least one place in each interval where the slope of the secant line, each of these secant lines, slope of each of these line segments, is equal to the derivative at some point in that interval, right? So that's awesome, because now, instead of writing delta xi, delta y sub I over delta x up here, we can really just write it as the derivative of our function evaluated at some point, x sub I star. We're squaring that, right? Okay, so that's what we've got. So I'm going to go back here and look back at this arc length. I'm going to replace this with what it is. So instead of I'm adding up all those lengths, but it's the same as adding up this expression. So adding up all of these, this is another way to just write. Actually, what I'm going to do is I'm going to put this delta x on the other side just to make it look a little more like something we've been studying. So this is 1 plus the derivative at x sub I star squared, and then times delta x, which is outside of the square root. All right, and so that's going to be a great approximation, right, for this arc length. But, as usual, if we take the limit as n goes to infinity, this is a Riemann sum. And so as n goes to infinity, our choice of our x sub I star really doesn't matter so much, because as n goes to infinity, these little intervals are going to get closer and closer together, right? So, and as they move closer and closer together, the x sub I stars are basically determined, because they're right. The endpoints of the interval are so close together, and x sub I star is in between the endpoints of those intervals, and so that just turns into the derivative at a point. So we end up finding through this process, a limiting process, that the arc length, which we'll call L, is actually equal to the limit as n goes to infinity which is really, by definition, an integral. So L is equal to the integral from a to b, the endpoints, square root of 1 plus f prime of x, right? It just turns into those x sub I stars. We're looking at the amount to taking derivative at a point squared dx. So that's the formula for finding the arc length of a function from a to b. And you can see really it's rooted in the Pythagorean theorem. It's also kind of a complicated integral. So sometimes it turns out to be easy to compute, and other times it turns out to be quite hard to compute. So let's do maybe an example or two, and yeah, we'll see what happens. So let's look at a couple of examples. All right, so I'm going to let f of x equal 2x to the 3 halves. And I want you to find the arc length over the interval from 0 to 1. So you might graph this from 0 to 1 if you wanted to. If I plug in 1, I get 2. And if you do some derivative tests, you can see that it's concave up. Ends up looking something like that from 0 to 1. Yeah, okay, so I can sort of I can tell you approximately what it is, right? I mean, for example, if I just drew a line segment here, I know that the length of that line segment is the square root of 1 squared plus 2 squared by the Pythagorean theorem, right? Which is the square root of 5, which is a little bit over 2, right? So this is sort of square root of 5, which is between 2 and 3. So I know that the length of the curve is probably greater than the length of that line segment. So just approximating my answer, I would expect my answer to be A little bit bigger than 2, definitely bigger than the square root of 5. So maybe like 2 point something. Anyway, we'll see what we get. So in order to calculate this arc length, right, we need to determine the derivative. So we know that the arc length is equal to the integral from 0 to 1, square root of 1 plus the derivative squared. So we need to find the derivative. Derivative, well, easy. That's just 3x to the 1/2. And we're just going to square that. Don't forget to square it. So that's just the square root of 1 plus 9x. We can determine that pretty easily. There's a very simple u substitution. If u is 1 plus 9x, dx is, 1/9 du. And so that turns into the integral from 1 to 10, right? If we plug in our x values into our u equation, we can determine the u values. And that's just the square root of u. So let's say u to the 1/2. And then 1/9 du. So I'm going to bring the 1/9 out here. Du. Okay, so that's 1/9. U to the, well, let's see. So it's u to the 3/2 divided by 3/2. So we get 2/3 u to the 3/2. Evaluated from 1 to 10. And so that looks like it's, 2/27. Then we get 10 to the 3/2 minus 1. And it's perfectly good. But if you plug that into your calculator, I think you'll get something like 2.268 units, which makes sense, right? We guessed that it was going to be something like that because it's slightly bigger than the square root of 5. Okay, let's do one more. All right, so let's find the arc length of, let's do y equals negative 1/2 x plus 25 from 1 to 4. Well, let's see. let's just do this. So, okay, so the arc length is going to be the integral from 1 to 4 square root of 1 plus the derivative of y. So we're dealing with, I guess we call it y here. So y prime squared dx. Okay. Should have done this one first. This one's easier. Okay, so the square root of 1 plus y prime is just, negative 1/2 squared. And so we just get, this is the square root of 1 plus 1/4, right? So 5/4. And that's just, I guess, square root of 5 over 2 x, evaluated from 1 to 4. And so we get, plug in 4, we get 2 square root of 5. Plug in 1, we get square root of 5 over 2, which amounts to, I guess we could combine these things and we get something like, that would be 3 square root of 5 over 2. So there you go, piece of cake. Let's see if it really, I guess, corresponds to what we would see geometrically. I mean, we can view this problem geometrically because we're dealing with a line segment. So let's look at the graph of this thing. So y equals negative 1/2 x plus 25. Well, it has a y-intercept of 25. I guess the x-intercept is going to be something like 12.5. So it looks like this. Keeps going, right? But we're only looking at it from 1 to 4. So let's say this is 1 and this is 4. So we're looking at the length of that piece of it right there. But it already is a line segment, right? And so we could just use the Pythagorean theorem on that. So we just need to know these lengths. Well, I know this is 3. And I just need to determine this length. But if I plug in 1 into my function, I get, right, if I plug a 1 in right here, I get 25 minus 1/2, which is 24.5. And if I plug 4 into my function, I get 25 minus 2. This is 23. So I guess the length of that little segment is 1.5. Okay, so the length of what we want, this line segment, is by the Pythagorean theorem, just the square root of 3 squared plus 1.5 squared. Right, and that's, I guess, 1.5. I really should call that 3/2. That would be easier to deal with. Right. Let's see. Yeah, so this is the square root of 9 plus 9/4. I can bring out a square root of 9, so I get 3 times the square root of 1 plus 1/4, which is 3 times the square root of 5/4, which is 3 times the square root of 5 over 2. Yeah, okay, cool. So our arc length formula works. Pretty awesome. Just to let you know that it doesn't always work out so nicely. I mean, the functions, the examples I've chosen are really pretty nice. I've chosen them carefully so that it all worked out. We could compute the integral. But, for example, say I wanted to find the arc length of f of x equals sine of x on 0 to pi. Right, so we could graph this sine of x from 0 to pi. Whoops. Looks like this. So here's 0, here's pi. We want to find the length of that piece of the sine curve. Well, okay, so it's not bad, right? The arc length is just the integral from 0 to pi, square root of 1 plus the derivative of our function squared with respect to x. And in our example here, we get, 0 to pi, the derivative of sine is cosine, so we get 1 plus cosine squared dx. And that's, if we can integrate that, that's the answer. Seems like we should be able to integrate that. It doesn't look too complicated. But, so, I'd encourage you to think about that for a minute, see if there's something you could do to integrate that. But, what you'll end up discovering is that nothing we've learned about in this class has prepared you to integrate something like this, right? So this integral is actually kind of complicated. The only way to really integrate this is to use some numerical techniques, some numerical approximations. It's the only way that I know of anyway. Yeah. So I guess the moral of the story here is that, well, two things. This arc length, the arc length of a curve can Well, if you don't choose your examples carefully, it can be quite hard, right? It can result in an integral that is pretty complicated. The formula has a square root of 1 plus something squared. It's not always an easy thing to integrate. Usually it's actually more likely to not be an easy thing to integrate in general. Also, the second thing is that out of everything we've learned in this class in terms of techniques for integrating, there are still integrals that we cannot determine, right? There's still some functions we can't integrate using the techniques that we've learned. So part of your continued studies in calculus will entail some ways to deal with complicated integrals such as this or other integrals, and part of that includes being able to use some more sort of numerical techniques to come up with as good of an approximation as you need. So, by the end of your next calculus class, you should be able to potentially approximate an integral like this to within as many decimal places as you want. Anyway, so that's it for arc length, and thanks for listening.